Well, it looks like it's official. We can get started. Welcome back. For today, we're going to finish off the last problem that we left behind in section 8.3. Then we'll be taking a look into the additional sections, 8.4 on simplifying rationals after we add, subtract, multiply them. And section 8.5 is going to be exclusively devoted to how to simplify rational expressions when division's involved. I do teach 1153. Thanks for asking about that. I have not taught 1143 in some time, though. I won't be teaching it next semester. Paget Jones, I know, is teaching an online version of that one. As for 1153, I usually teach that one in the fall semester. I'm currently teaching it right now. Yep, absolutely. So with what we've got going on for today, we have our quiz number 8 due. That one's based off the application section. I believe that was section 7.5. And quiz number 9 is going to be based off the section 8.3, simplifying rational exponents. Well, any other questions before we take a look in section 8.3? Okay, let's get started. Hopefully we get some others to join, but I appreciate it that you made it in today. It's usually not easy to make it into this particular class right before Halloween, but we're here, we'll get through it. And here's where we left off. So we were looking into exponent laws as they relate to dealing with rational exponents. And on this one right here, the major idea was we just took the exponent of 4/5, distributed it to these two different bases, and rose them both to the same exponent 4/5. The next major idea for the exponent laws was after we use this first exponent law, that a times b to a power m is a power of m, b power of m. The next exponent law on this line was that a to the power of n raised to a power of m becomes a to the power of n times m. And this was kind of the punchline with the second half of the notes in section 8.3. We're just revisiting the exponent laws, and we're only using the idea that m and n can now be fractions. After we use that exponent law to multiply 4/5 and 3, we got down to this line by just using the exponent law of if we see something with a negative power, a power negative n, we can rewrite it as 1 over a to the power positive n. We'll try to several more exponent laws on this one down below. And here's how part E goes. First thing we probably want to do is, well, you kind of have a lot of options with these. You could simplify on the inside, force the exponent to be positive. Let's go for the positive exponent. That's going to be an assumption when we write down our answers that's only involving positive exponents. So we can use this exponent property. A fraction ab to the power negative n can be rewritten as a fraction b over a. So flip the fraction, take the reciprocal, and convert the exponent to a positive n. So this entire thing right here can turn into a positive exponent, 5/2. When we flip the fraction, the tricky thing is we copy this down verbatim. It's now the numerator, but the exponents don't change to a negative version. Just like over here, there's nothing changing. A is just directly copied to the denominator. B is just directly copied up into the numerator. So our new numerator was the old denominator, written in verbatim, x power 1/2, y power 2/3. And our numerator here becomes the denominator, x squared, y power 1/3. Then we can raise all four things inside here, the two factors in the numerator to the two factors in the denominator, to the power 5/2, but that's working a lot harder than we really have to. If we simplify inside the fraction, then the next step becomes easier. And there's two kinds of things we can simplify. There's a like base, x and x, like base, y and y. As we go to simplify those, we're just using more properties of exponents. So let's focus first on base x. X power 1/2 divided by x squared. We want to go for an answer with positive exponents, so we should use the power that goes like this. Or excuse me, use the rule that goes like this. A power n over a power m is 1 over a power m minus n. So in other words, we're going to subtract 1/2 from the power 2 in the denominator just because it's larger, giving us a larger exponent. So we'll have 1 over that x squared we have, we can rewrite as a 4/2 minus a 1/2. So power 2 changes to 4/2. We're subtracting just like this indicates by subtracting the 1/2. And we get 1 over x power 3/2. It's in the denominator, so when we go to write it in, we just drop it down here. X power 3/2. Let me kind of center that better. There's lots going on as soon as we put in new fractions. It feels like it's such a bigger problem because now we're dealing with the fraction arithmetic at the same time that we're dealing with the exponent laws. So sometimes it's a good idea to kind of separate out the problems. Do a chunk like this, handling base x on the margin, then just throw it back in. Following that same strategy, let's do the chunk, the thing involving power y, or base y, over here as well, y power 2/3 divided by y power 1/3. This one's a little nicer because it has the least common denominator already. The exponent law we'll use on this one is a power of n divided by a power of m. Same setup, but there's two ways you can do it. You can keep the power or the base in the denominator, but this time the exponent's larger than the numerator, so it's better to keep the base in the numerator for this one. That way we don't have an extra negative exponent we have to correct as an extra step. So this will be a power n minus n for the numerator. Working it out for this one, this will be y power 2/3 minus 1/3. That just gives us y power 1/3 altogether. So up into this numerator, we have y power 1/3. Then whole thing is raised to power 5/2. And at this stage, part E is very, very similar to what we did on the prior part. We had two bases, base x, base z, raised to an outer exponent of 5/2. We just took each part, each factor, and raised it to that exponent, and then multiplied the exponents together. It'll go the same way whether it's being multiplied or divided, so same kind of concept. So in our next line, this becomes y power 1/3 raised to the power 5/2. Then down below, x power 3/2 raised to power 5/2. Then all these exponents do is multiply together. So just to do these out in the margin for the sake of being careful with the fractions, for base y, it's 1/3 times 5/2. Nothing reduces in that configuration, so just multiply across tops and bottoms, and we get power 5/6. Then same exact idea with base x, just different fractions. Take 3/2, multiply it by 5/2. Yeah, nothing simplifies on this one either, so we're just going to get 15/4. So 15/4 copies in, and that's where the problem finally ends. Again, it looks a lot worse because fractions are everywhere, but in principle, it's the same kind of problem from the ones we saw in section 5.2. Same exact exponent laws, but now fractions in the mix. Well, any last questions running through these problems, this problem here? Okay, next section, we're going back to square roots like we were seeing them in sections 8.1 and 8.2. 8.3 is kind of a weird section when you think about it. The major takeaway with section 8.3 is that this idea is often very beneficial, that an nth root can be considered an exponent, a to the power of 1 over n. And if it's an exponent to a full-on fraction, m divided by n as your exponent, you can just take the nth root, raise the result to power m. Then, just because we were thinking about fractions as exponents, that's the major reason we did these kind of problems here and the ones we just finished. Now returning to really the major topic of chapter 8, we're going to deal with simplifying square roots some more. And that's a good idea because it feels like section 8.2 is a short one. We're just returning back to that same kind of content, slightly different concepts thrown in, but focusing on simplifying roots again. So first, just as a warm-up, we're going to look into the concept of adding like terms. These are things that are considered, we can take for granted that being in this class means you have a good understanding of how this works. But just for the sake of being really careful with the new concept like radicals, this is a pretty good warm-up problem for us to begin. The warm-up just says add the like terms, and the only like terms in part A are the ones involving x power 2. To be like terms, we have to involve the same variables raised to the exact same powers. That means 8x and 6x squared are unlike terms only because the power on x itself is different. So when we go to add these together, essentially what we're doing is some clever factoring. We usually don't show this step, but just for the sake of really thinking about like terms, the reason we can add these two, but not the last two, is because there's a greatest common factor with 3x squared and 6x squared. You can factor out x squared, and we would traditionally factor this out to the right-hand side. Usually we factor to the left, but in this case, x is factored to the right-hand side. Then we can just add up the coefficients. 3 plus 6 will give us 9x squared plus 8x. Again, we usually just skip from over here. 3x squared plus 6 more x squared gives us 9x squared total. But this is the rationale of how it really works. It's just factoring out the greatest common factor. Likewise, in part B, this looks like something you would get if you FOILed out something. 3x squared is not like term to anything else because this is a different power on x. And the constant term doesn't involve x whatsoever. Likewise, 4 is not a like term to anything else for the same reason. It doesn't involve a variable, so we can't add it to anything here. But the middle two terms are like terms. If we did this extra step here, you could factor out x from both of these. But this is how it would be done traditionally. This is how we've been doing it all class. We would say, take 3x squared. Then if you have negative 8x plus 9x, you would get 1x, but we typically write that as just x. And then plus 4. So that's our warm-up, and now we're going to go over to the new concept, like radicals. Any questions with the warm-up problem so far? Okay, well, the connection between ordinary adding like terms, as we know and we've used so far semester, and like radicals is that we had like terms if the terms involve the same variable raised to the same power. For like radicals, we consider the radicals to be like if they have, well, what's the analogous thing to the same power? That would be the same index. The root you're taking has to be identical. So this index and this index has to be the same. And you know that really is a power, much like x squared or power x, because the nth root of a is really a to the power of 1 over n. So for these to be truly like terms, you have to have the indexes identical. N must be m. And the other thing that's important wasn't just the powers being the same, it was also the fact that you had the same variables being the same to make the like terms. For square root symbols, the analogous concept is the radicands, a and b, have to also be identical. That's much like saying you have to have the same variable x raised to the same exact powers, the index. So the concept feels different if we talk about like radicals, especially if it's written as a root like this is. But if we relate it back to the last section, write them in exponent form with a rational exponent, really it's just the same concept about like terms exactly as we've seen it before. Well, here's how they go. Example 2 says simplify. We're going to make the assumption that all variables represent positive real numbers when we encounter them. And really, it's just kind of the same thing as before. When we added, say, 3x squared and 6x squared, it's no different than dealing with square root 3 minus 4 square root 3. we have the same radicands, the 3's here. The indexes are the same. They're both implied to be an index of 2, taking a square root. So the whole punchline to this problem says this is really one copy of square root 3 minus 4 copies, and you get -3 square root 3 altogether. Then the whole problem ends right at that step. If you wanted to, you could visualize this in a different format. Much like you could have factored up here, you could factor this as well by saying, take out the square root of 3. It's common to both terms, the first and the second. If you factor out square root of 3 here, you'd get a 1. Factor out square root of 3 here, you get a -4. But then you'll notice we're doing the same exact thing. We're just putting in an extra step for no apparent reason. And still 1 minus 4 for a -3 times the square root of 3. So we usually do it in this way, not showing the middle step. But this is the logic of why they had to be like radicals in the first place. Just like up here, it forces them to be like terms. Well, that's the major things we're going to be getting into in section 8.4, adding and subtracting radical expressions, whether they're square roots or otherwise. Any questions with the first part, A? Okay, part B is not too different. There's more terms, so there's more stuff we have to look for and be careful with. They're all square roots, so that would be like everything here having a power 2. But the radicands are different. So that'd be like this having powers 2 everywhere, except the variables go x, y, z. If that's the case, then there's no like terms whatsoever. So we have to be careful with these two parts. These are the only two like roots that we'll see. And plus 9 root 10, it just sort of comes along for the ride. So this turns into 5 copies of square root of 2 plus 3 more copies gives us 8 square root of 2. This one is unlike because the radicand is different, so we just go plus 9 root 10. At that stage, the whole problem is over, so these go pretty fast. Really, the only way to make this a more computationally intensive kind of problem is if you just make it so the roots have to simplify, like in this version right here. A little bit more going on with this stuff here, so we'll be a little bit more careful with this one. Well, the 9 here can't simplify as far as cube roots go. That one has an index of 3. If it was a 27, we could simplify it. But x power 5 does reduce because the exponent of 5 is higher than the index of 3. This is probably the most annoying part of the problem. We have to deal with the 72 as well. Reducing things when they're integers is a little bit more involved. But x squared, this part right here can't reduce any further because the index is now less than, the power of 2 is less than the index of 3. So x power 5 will reduce, x power 2 here and here won't reduce. Let's deal with the 72 first, just to get us started. 72. We can factor this down to find the prime factors. We're looking for triples because we're taking a cube root. First 2 divides goes in 36 times. 2 divides that 18 times. We've got a triple, 2 divides 18 9 times. And 9 is 3 times 3, so that one can't reduce under a cube root, just like this 9 couldn't over here. So best way to factor 72 when we're dealing with a cube root is to write this as 2 power 3 times 9. So coming back down below here, let's rewrite all of these terms. We have 5 times the cube root. You have to be kind of careful how you write these cube roots so we don't accidentally make it look like we rose 5 to the power 3. So let me kind of write it sort of like this. Just give an extra placeholder for the cube root. Now it's not going to be something we mix up as 5 cubed on accident. So the 9's just fine where it is. X power 5 we can factor as x cubed times x squared. Then if we factor in that kind of way, the x cubed can reduce. The x squared is the part that's going to stay behind. Then go plus 2x. Another cube root. Another strategy is put a little space, and that also avoids the confusion. We don't mean x cubed. We mean 2x times the cube root of something. For 72, we're putting in 2 power 3 times 9. Something went wrong with the 9. Let me fix that. Times 9 times x squared. Then it's just a minus 3x times the cube root of x squared. So with what we've got all set up, we have two things that are going to reduce. This x cubed will come out as just an x, and 2 power 3 will reduce as well as just a 2. Everything else is just trapped inside the cube root expression. So first step was just organizing, factor things down. Sometimes use a full-on factor tree if you need to, if the integers are large. Now we reduce all three radicals. Well, except for this one. This one's already as reduced as it gets. First we have 5 times cube root of x cubed. The index of 3 just divides this 3, leaving behind x itself. Then it's 5x times cube root of 9x squared. Then another reduction, here we have 2x, just copied in, times, same idea as before, the cube root of 2 cubed, well, that's really just the cube root of 8, gives us a 2 altogether. So 2 pops outside, and we leave behind cube root 9x squared. Then we have a negative 3x cube root of x squared. This next step is kind of painful, but just for the sake of seeing this nicely, I want to take one more step to multiply 2 times 2 to make this a 4x. So this is just full-on copying 5x cube root 9x squared plus 4x cube root 9x squared minus 3x times the cube root of x squared. Okay, now everything is completely simplified, including that small simplification. If you just put an eraser here and wrote in 4x, that would have been understandable. That'd be a nice shortcut to take. Makes the notes confusing, so we took the extra step to put in the 4x. And now the thing to notice is we have 9x squared here and here. That's good. They're both cube roots as well, so they're like roots. But this one's no good to us. Sure, it has x squared, but if it's missing the 9, that one is not a like root. This is much like the 9 root 10. It's just going to come along for the ride, but there's nothing we can do with it. We have 5x plus 4x, so altogether we have 9x's multiplied by the cube root of 9x squared. Then copy down minus 3x cube root x squared. So this is the one where we focused on reducing the roots as well, just as a kind of a extra practice from what we did in section 8.2. The major concept then is just adding up the like terms after we simplify the roots. Well, any questions, folks, with getting through example 2? Okay, some of these go pretty fast, like we've seen, like parts A and B. Some of them take a little bit extra time. Just organize, simplify them down as much as possible, and then identify which ones are like. And then it becomes a problem just like parts A, part B. So the next concept we're going to get into, which is, again, just more reducing roots, is to take another look at this formula here. This is kind of like deja vu. This is a formula used directly in section 8.2. But let's look at the way we actually use that formula. So let's take a bit of a mental break and remind ourselves that when we're in section 8.2, this is essentially what we were doing with this top formula, the multiplication formula for roots. We took something that was already multiplied, we factored them, then we split up the factors so we could reduce one completely, and then leave the one that doesn't reduce totally behind. Similarly in part B, we split up these factors. The things in green were the ones that simplified, the ones in blue were the ones that stayed behind. We did it more with fractions in this kind of form as well, but we'll come back to this topic in section 8.5. Fractions have its little own thing that we have to worry about. The major takeaway is it's the same formula. We're just going in a different direction this time. In section 8.2, it's written this way. And in section 8.4, same formula, but it's backwards now. That's because we're taking the roots and now multiplying them together. So we're going in the opposite direction. In fact, it's still an 8.2 problem because if we take these two things and multiply them together, same formula we've been using before says this is going to be 5 times 10. So now it's the square root of 50. But once we get square root of 50, we need this formula again, just like we saw in section 8.2. Sorry, let me try to minimize that. There we go. We're going to simplify again, just like in section 8.2, like even with this problem right here, by splitting up the roots again and simplifying square root 50. So the first step tells us we can take two square roots. The indexes have to be the same, but the radicands can be different. We just multiply whatever they are together, keep the common root. It was a square root in this problem. But after we do that, we do have to simplify our result. This one's not too bad because 50 factors in a nice, clean way, 25 times 2. 25 is the thing that's going to be reduced. 2 is the thing that stays behind. And sometimes we do skip a step here and just write this as 5 root 2. But just to emphasize we're using this formula twice, we can now rewrite this as square root 25 times the square root of 2. So it splits in this way again. So we use the formula to put them together. They didn't reduce alone. 10 is 2 times 5. 5 is not going to reduce as a prime number. But once we put them together, they suddenly do reduce. And then we split them up again. It's like we're just reordering what gets the 5 and 5 to make up the 25. So we can simplify this part. This just turns into now 5 square root 2. And again, often when we do this kind of problem, we skip to this step. So this is a common shortcut. So this is the punchline to all the problems in this second part of the section notes. We'll look into different versions of this, some getting a little bit trickier than others, where the major feature is we use the formula and then practice simplifying just like we did in section 8.2. Any questions at the moment before we try a few more? Okay, next one looks a little bit more gnarly because now it's a fifth root, but that's okay. It doesn't really matter what the index is. The major thing is the index has to be identical, like it's indicated in this formula. So if you have the same index here and here, you copy that same index over here, and all you're doing is multiplying together what's under the root, the so-called radicand. Well, radicands, I guess, would be plural on this one. So this turns into the fifth root of 8u power 4 times 4 u power 8. So that's what happens when we multiply these together. Here's the multiplication. Let's simplify this further by actually multiplying them. 8 times 4 gives us the 32. And this turns into u to the power of 12 altogether when we combine the like bases. 32 feels like deja vu. We've explored this several times. 2 to the power 5 comes out as a 32. That's convenient for us because that makes taking the fifth root pretty rapid. But u power 10 is no good to us. That one we should factor down. So we can rewrite this as 32 is now 2 power 5. Don't forget the fifth root symbol goes here. U power 12 is a problem because 5 doesn't divide it evenly. So drop to the power 2. You get 10. Now 5 divides that evenly, but you have to counterbalance that by putting in u squared, so that this equality here is truth, not saying a lie. So this part and this part will both simplify. U power 2 will stay inside the fifth root. And mentioning this common shortcut, this is a very typical way the next step would be written in. We'll take the fifth root of 2 power 5. That gives us just 2 altogether. Here, the index of 5 divides u to the power 10. So it becomes u to the power of 10 fifths. And if all you put here was u squared, that'd be completely fine as well. And what stays behind is the fifth root of u squared. With the way I wrote this, I do have to write in an additional step. So this now becomes 2u squared times the fifth root of u squared. And same sort of comment as we did on part A. Going from here to here, just writing that in, is a common shortcut. Or maybe let's target this arrow a little bit better. Going from u power 10 inside the radical to just u squared, because we knew the power 10 was going to be divided by the index 5, if you just jumped here to u squared, then that's a very common shortcut as well. But we're in part viewing this section as kind of a review of section 8.2. So we're showing some of these things again. So that's 2 down. We'll take a look into the next one, where we have to use the distributive law this time out of nowhere. Any questions on part B? Okay, well, here's how part B goes. Like we mentioned, first is the distributive law. We can multiply cube root of 5 and cube root of 100 and get cube root of 5 times 100. They multiply inside one common root because the indexes are both 3s. If this was a fourth root, then the 5 couldn't have gone inside there. Then just multiply again, multiply here to here. We have minus 1 overall cube root of 5 times 75. And you could have written, say, 500 right here. You could have done the same thing with 5 times 75, but it's actually better that we didn't, because we have to simplify these things down. And a big punchline to how these simplify nicely is we just get their prime factorizations. So let's work on both of these simultaneously. We'll save part D for next. Prime factorization of 100, well, it's going to involve 5. It's going to be a couple factors of 5. So that's going to make up 5 to the power 3. We just have to see what's left behind. So we can divide it by 2 first to get 50, 2 again to get 25, and then it's 5 times 5. So for our purposes dealing with the cube root, the factors 2 aren't beneficial because it's not a triple. So we'll just write this in as 4 times 5 squared. And then same exact thing for the 75. 75, well, first 3 divides this, going in 25 times. 25 is 5 by 5. So this is 3 times 5 squared. So we can now put in those 2 factorizations. On the first term, it's cube root 5 times. 100 we can rewrite as 4 times 5 cubed. Excuse me, not quite cubed yet. Let's see what we just did. It was 5 squared. I think I was thinking it'll eventually be cubed, but not right at that step just yet. Then do it again. It's minus cube root 5 times 75. 75 here gave us the 3 times 5 squared. Now we can start to recombine these slightly differently. This is cube root of, on the very first term, that's 5 cubed times 4. On the second term, we have the cube root of 5 cubed again times 3. So this is the part that simplifies, as well as this part. The part that stays behind, the part that's just going to be an irrational number, is 4 on the first term, 3 on the second term. This means we're just about there. Cube root of 5 power 3 is just a 5. That's the cube root of 125 if we were to multiply that out. Leaves behind the cube root of 4. Then one more time, We get a 5 again, just like before. Times the cube root of 3. And at this stage, it becomes kind of a dangerous problem, say on exams. A common thing that could happen on, say, this would be a third exam problem, is you might say that this is 0. And to some sense, that does seem kind of logical. Sure, 5 minus 5 is 0, but we have to know that it must stop right at this step, where we might lose a point on this problem. The reason it stops right here is these are not like roots. Sure, they're both cube roots, but the radicands 4 and 3 are different. So the problem has to end right at this step. So that's a good thing just to write down as a word of warning. These ones are not like roots. Which implies we must stop here. That deserves an exclamation mark, I would say. Well, this one was more tricky because we had to use the distributive law. Then we were really simplifying 2 roots at the same time, 2 cube roots. We'll try out another version before we move it to the next question or the next concept. And that's this part D right here. This one is pretty dangerous as far as it would go if it was on a real exam situation. What makes part D a tremendously potentially tricky and dangerous problem is you could spend a lot of time on part D by accident. The reason for that is you can simplify this square root independently of this square root. But simplifying this square root is a pretty big problem in its own right. Simplifying this one is a big problem in its own right. Then you have to multiply the results together, and that's not guaranteed to be fully simplified either. There might be a third simplification you have to do. So this is one of those problems where you could be spinning your wheels for quite a while. And if you do get the right answer, you might have tripled the work we're about to put down. The best thing to do is put them together first. If we multiply the square roots together, then we just will have one square root we're simplifying altogether, not potentially up to 3 different square roots. So absolute best thing to do, this one deserves a comment because again, seeing this one, similar versions of this on exam, this has been a tricky problem. I can't say the word must because you could do it differently. It just takes a lot longer. We can save a gargantuan amount of time. This is a better way to say it. By multiplying the roots first. I think that deserves an exclamation mark too on this one. So if we multiply the roots together, here's what it would look like. You would just take 5 times 30, that's going to give us 150. Then x power 5 times x will give us x power 6. And that's nice because that's an even exponent. The index of 2 is just going to give us x cubed when we go to simplify this. Y power 3 times y power 2 is y power 5. Not as nice, but we can fix that pretty fast. Really, most of the work at this stage is just factoring 150. So let's take a look into that next factorization. We're looking for pairs of factors because we're dealing with the square root this time. 2 goes inside 150. Let's see. 75 times. Then at that stage, 3 divides. 3 goes into 75 25 times. And well, 25 is a perfect square, 5 times 5. You could either write it as 5 squared, kind of like how we wrote in the 5 cubed, or a different style of doing this is you could just leave it as a 25. Let's leave it as a 25 just to show an alternate way to write this in. There's no repeat of factors 2 and 3, so let's just multiply them together. We get a 6 out of that, times 25. So the 150 now splits apart as 6 times 25, x power 6. We need to do another factorization for y power 5. Let's drop it by 1 power to get a power 4 times y. Then the good stuff, the stuff that actually reduces by the square root, giving us an exact number, is the 25x power 6 and y power 4. That's because the index is 2, and all these things highlighted in green have a power of 2. 25 is just really 5 squared. Or I said a power 2. Better to say a power that's divisible by 2, an even power. The stuff that stays behind will be just the 6y. So now all we have to do is write down the answer. You didn't have to write in the index of 2, but penning that in sometimes is not bad as a reminder. The square root of 25 comes out as a 5. 2 divides here, leaving x cubed. Divides here, leaving y squared. And all that's left behind is square root 6y. This stage, we're totally done, and this is doing this problem as fast as possible. Well, any last questions, folks, about the concept of multiplying the roots together? Okay, well, we want to expand a little bit more on what we did in part C. We used the distributive law. That's because the factor to the right had 2 different terms. But if the factor to the left, right here, had 2 different terms, we're still using the distributive law, but we're using essentially the FOIL method to make it happen. And that's what the next problem is all about. We're going to start FOILing out square root expressions like the ones we see down here. And when that happens, there's a really handy formula that helps us out a lot. It comes in really 3 different kinds of formats. You can take the square root of a squared. If a is positive, there's no absolute values here. The square root of a squared would give you just back an a. In a slightly different kind of format, if you take the square root of a times the square root of a, you get just a itself. And yet again, in a slightly different format, square root of a times square root of a in terms of exponents is just square root of a squared. If you square a square root, you get just a back again. So a quick example involving some of these ideas could look like this. If you take square root of 17 times the square root of 17, well, this could be rewritten as the square root of 17 times 17. It could also be expressed as the square root of 17 power 2. So that's this formula we're thinking of. But if you undo the exponent, square root of 17 power 2 just means multiply square root of 17 by itself. The formulas we were just looking into say you can multiply these together, take 17 times 17 on the inside. That would be the square root of 17 squared. But we've dealt with this kind of situation before. The index of 2 that's right here would cancel this power 2, and it would leave you with just a 17. At no stage did we really have to take 17 times 17 and get a large number out. The moment we saw this, that's 17 as well. So this was equal to 17. The moment we saw root 17 times root 17, we could have just put in 17 as well. And if it's root 17 squared like this, it's 17 just as well. But these are the ones we're going to see a lot, it turns out. A root times itself, root 17 times root 17, will give you back 17. We don't have to work hard on it. This is just a foregone conclusion. So here's how it comes into play on the example below. If we're going to multiply these root expressions that have multiple terms, we'd be using the FOIL method. First, we multiply here to here. And when we do that result, we'll take the 5 times 7 first, the ordinary multiplication, to get 35. Then it's going to be square root of 2 times square root of 6. If you call that square root of 12, that would have been a great idea. That could have saved a step. But we'll build this up in stages and then multiply here to here. This one starts off the same. You take 5 times negative 8 to get negative 40. But it's a little bit different. It's also square root of 2 times square root of 2. That's no different than root 17 times root 17. When we multiply root 2 times root 2, that would just give us a 2 back. And so we save a lot of time just writing it in that kind of form. Then we keep on foiling, we multiply here to here. This will be plus. Take the coefficients, 2 times 7 to start. It's going to be a 14 times, well, now it's the square root of 6 times the square root of 6. If you work this out, square root of 6 times the square root of 6, you might have said that this is the square root of 6 times 6, which is the square root of 36. But the square root of 36 is 6. And that's the idea of this really nice formula. You don't have to turn it into a lot of steps. A root times itself is just going to give you that radicand 6 itself, as long as it's a square root. If that was a cube root, it goes a little bit differently. So we'll see what happens when it's a cube root like this one down below. But so far, we're just about done. We just have to multiply here to here. This is going to be 2 times -8 to start, so -16. Square root of 6 times square root of 2. Now we're just simplifying what we got. On the first term, this was 35. Root 2 times root 6 is root 12, multiplying those two radicands on the inside. Then it's minus 80. This will be 60 plus 24, so plus 84. Minus 16 times root 12 again. Then the next thing that happens is we have to simplify our roots whenever they occur. So root 12 will simplify. Let's do it on the margin over here. Square root of 12 can be rewritten as square root of 4 times 3. This becomes square root of 4 times square root of 3. So this is just a 2 root 3 altogether. So that's what we're going to put inside the root 12s when they occur. On the next line, this becomes 35 times square root of 12 was 2 root 3. We have like terms in the middle. -80 plus 84 gives us positive 4. Then go minus 16 times 2 root 3 again. Almost done. This one turns into, looks like it has a lot of steps to get through. Multiplying these integers, 35 times 2 gives us 70 root 3. Then we can't take 4 minus 16. Order of operations says you have to multiply there. So go plus 4 minus 32 root 3. But then this becomes a problem like example 1, part A at the very start of the notes. We have like roots out of nowhere. This is square root 3, a square root 3. So if you have 70 copies of root 3 minus 32 copies of root 3, you're left with, let's see, 38 copies of square root of 3. Just taking 70 minus the 32, then it's a plus 4. Whew, we did it, folks. This involved lots of square roots multiplying together. We used these ideas as a way to simplify the process so we didn't get too bogged down. Then we had to simplify the root 12s in the middle as well. So that was the additional concept to get through the problem. Once we did all that, add the like roots together. We'll subtract them on this problem rather. And this is where it settles. We'll try it out on the next version, but any questions at all with part A? Okay, part B turns out to be something really special that we need in the next section, 8.5. Notice it kind of looks like the same exact problem, or the same exact factor rather. 8x root 5 minus root 11, x root 5 plus root 11. The only differences are the signs in the middle. And when this happens, it might remind you of a plus b times a minus b situation. If you FOIL this out, you get the difference of squares, a squared minus b squared. That was one of our major factoring formulas, as we saw it in chapter 6. So that's kind of nice in a way. When it comes up in this context with roots, we call this a conjugate pair. A conjugate pair occurs when the only difference between the pair of factors is that the signs in the middle are opposites. But when you FOIL out a conjugate pair, like in this situation, you're squaring the first term, you're squaring the second term, and you know if you square a square root, it gives you back the thing inside. The square root itself just vanishes. So this is something that starts with square roots, just like in the last problem. But because it's a conjugate pair, there's going to be no square roots when we finalize FOILing this thing out. So here's how it comes together. First, you multiply here to here. That's x times x for an x squared. But then it's root 5 times itself, root 5. That's just going to be a times 5 altogether. Now, this is the step that you don't necessarily have to write down. The middle terms canceled over here, and they also are going to cancel over here. If you take x root 5 times root 11 and write it down, here's what it looks like. Here's what it would look like, x root 5 times root 11. But then you immediately have to multiply negative root 11 into x root 5. So this will become negative root 11 times x root 5. The order of the factors are different, but that doesn't matter in multiplication. These are like terms, and they cancel immediately. Next thing is to take negative root 11 times positive root 11, gives you a negative value, and root 11 times root 11 is just 11 itself. So middle terms cancel, and all we're left with is 5x squared minus 11. Kind of refreshing after doing this long problem that had a lot of steps. So again, then we're going to come back to this conjugate pair when we go into section 8.5, simplifying square roots in the context of division. But for the moment, it's kind of a neat trick. It's a way to vanish square roots when they occur. This one is also tricky because remember, there's no exponent laws that says if you were to multiply this out, you get 5 squared minus the root of 10 squared. This one we have to actually write out in this form. 5 minus root 10 times 5 plus root 10. And much like the factorization section for the difference of squares, this is another idea where a plus b squared always writes out as a squared plus 2ab plus b squared. So if we FOIL this out by expanding, this is what we would get, 3 terms in total. The way you would do it is write a plus b twice and then FOIL it out. And that's what we're doing over here when we multiply this one. But then at this stage, it's just like before. You take 5 times 5 for 25. Here to here is going to be plus 5 root 10. And I think I did make a mistake. Let me fix this. That was supposed to be a minus on both. Let me highlight the sign just for emphasis. So that should have been on my last problem, negative 5 root 10. Okay, then FOIL further, multiply here to here. That's going to be negative 5 root 10 again. And then the last multiplication, negative root 10 times negative root 10. Signs cancel to positive, and root 10 times root 10 just gives you 10 together. Now we have two kinds of like terms, 25 plus 10 giving us 35. And we have like roots again. They're both square roots with a radicand of 10, so negative 5 root 10 minus 5 more copies gives us negative 10 root 10. Then that's where the problem would end on this one. Another fast one, just like part B, a little bit more work because the middle term doesn't just simply vanish, but that's how either one will go. Really, it's kind of like the old formulas we saw before in the factoring section. Then part D is something entirely different. There's a cube root here, so this property of taking, say, root 11 times root 11 to get 11, that only works for square roots, unfortunately. The formula up here is very specific. This is a power 2 here. These are all square roots. Without the square roots, these formulas completely break down. You'd have to change them up. And the context of FOILing, there's no really nice way to change this up. This one's just a slightly more complicated expression that we have to work out carefully. So let's FOIL out this next one. First, we take the cube root of 4x times the cube root of 4x. That's going to be 1 cube root. 4x times 4x multiplies together to give us 16. x squared. Then multiply here to here. That's going to be negative 3 times the cube root of 4x. The last part to FOIL will be here to here. That's going to be positive 3 times the cube root of 4x. So they are in a certain sense a conjugate pair. The middle terms do cancel, but because they're a cube root, the root itself won't vanish on this one. This one is just going to simplify a little bit further. Last thing to do is positive 3 times negative 3 for a negative 9. But even though it's not going to eliminate all the cube roots, it's nice that these two eliminate. They have opposite signs. They're like roots, so those parts are gone from the problem. Last thing to do is just reduce the cube root of 16, which isn't too bad. We can rewrite 16 as 2 times 8, which is 2 times 4, which is 2 times 2. So one way to write 16 is 2 power 4. But for taking a cube root, the best way to write 16 is 2 cubed times 2. We want to exhibit the triple since this is where the reduction is going to occur on 2 power 3. So let's rewrite this as cube root 2 power 3 times 2 x squared minus 9. It's just another reduction of a root, a cube root this time. This part reduces, and this is the part that stays behind, that can't reduce any further. So one last reduction, 2 to the power 3, take the cube root of that, and you just get 2 to the power 1. Best way to write that is just a 2. Left behind is the cube root of 2x squared, and then subtract 9. And that's the whole story to part B. If we were to FOIL all these out carefully like we just did, we have to reduce in the middle, combine the like roots, and this is the answer we'd get. Well, any last questions, folks, on finishing 8.4? Okay, with the last bit of our time we have, we'll take a quick look into section 8.5, not with the goal to race through it, but just to see what this section is all about, and maybe do a few problems in section 8.5 before we call it a night. We can kind of see why 8.5 is sort of its own section. It wasn't in the last section. The last section we added, subtracted, multiplied radical expressions, but we did not divide them, because when it comes to divisions of radical expressions, and when the instructions say to simplify, simplify suddenly becomes a pretty overloaded statement. This is extremely context sensitive. If we have a radical expression and we say to simplify, there's a lot of different assumptions that we're going to make. Any radical expression in which the radicand is written as a product of prime factors is what we want to consider. Then the expression's in simplified form if all the following conditions are met, all three simultaneously. So we cannot have a radicand, or the radicand has no factor to a power greater than or equal to the index. If that happens, it's not simplified. And that's what's gone wrong with the cube root of y power 5. We have a power here. Actually, we usually have been highlighting yellow for the index. We have a power here of 5, which is greater than the index of 3 in this problem. That tells us this one doesn't simplify. We'd have to do some work to simplify that one. For the second version, this almost feels kind of unfair. It looks pretty simplified. 7/3 doesn't reduce. But we're going for a kind of standardized answer when we have simplified roots and division occurs. So the major thing we're trying to eliminate is the fraction. So if there's a fraction inside of our root expression, we consider this to be not simplified. And it didn't matter if it was a square root, fourth root, fifth root, and so on. The fact that there's a fraction at all is the whole problem with that one. So it cannot contain a fraction. That's our issue here. We'll see how to correct those when they occur. And for the last part of the problem, this is where the conjugate comes into play. No radicals can be in the denominator of a fraction. So when there's a root right here, this was the one part that makes it not simplified. So we're going to look into how these simplify. We're going to take advantage, especially in example 1, of the property that says the nth root of A over the nth root of B can be re-expressed as one gigantic nth root of A over B. So that's what this section is all about. Really, the first part here are things we were looking into in the very last section. Part 2 and part 3 of what we mean by simplified radical are the things that are new to section 8.5 specifically. So, for example, right here in example 1, we know automatically this one's not simplified because there's a radical expression in the denominator, square root of 6x power 5. This reduces, you can reduce the x power 5 inside of this, but this would be working really, really hard because you'd have to reduce this independently of the numerator. And after you do 2 reduction problems, the thing you get still might reduce even further. Best thing to do is just put them all together, like we were mentioning with the product rules. If we put this together, we can write 1 over all square root, 78 x power 21, 6 x power 5, and just reduce the fraction that we see. 6 goes into 78, let's see, 13 times. And I think I wrote the square root symbol kind of strange. This looks a little bit more appropriate. This looks like an even division. 6 goes into 78 13 times. X power 5 goes into x power 21, x to the power of 16 many times. 13 is a prime number, so this one doesn't reduce, but x power 16 would reduce. The index is 2, so we'll divide into the 16, and we get, as an overall answer to this one, x power 8 times the square root of 13. So the 13 would just copy into this one. At this stage, it is simplified. Root 13 is to a power of 1. It doesn't factor down. There's no denominator inside here. Root 13 isn't in a denominator itself. So there's nothing further to do with this one. So it's a fantastic formula. It tells us we can just put roots together and simplify from there. Let's try out the same idea in part B. If we put the cube roots together, we get 1 overall cube root of, first let's treat ourselves to a calculator on this one, 162 divide by 3 would give us a 54. So 54 stays in the numerator of this one. Actually, let me write it this way just to show the step. 162 y power 9, 3y power 2. Feels like I was doing too much in one step. Now let me actually do the division on the next line. This turns into the cube root. 3 into 162 went in 54 times. Let's double check that result. Yeah, it looks like a 54. Y squared goes into y power 9, y power 7 times. Next, we can factor 54 in this kind of way. 54 is really just 2 times 27. 27 is 3 times 3 times 3 for a perfect cube. So this one reduces down to just a 3. Y to the power 7 is not good for us, but we can rewrite this as y power 6 times y. That gives us y power 7. And that's a power 6 that's divisible by 3. Oh, and don't do as I did. Definitely write in the index of 3 to remind yourself that's a cube root. Then this one is immediately satisfied at this point. 27 is 3 to the power 3, so its cube root is just 3. The index of 3 divides this one, leaving behind y squared. And all that's left over is just now the cube root of 2y. So that's 2 down. I think we have 1 more. Nope, that's it for that set. Example 2 is slightly different. That's the 7/3 that we saw here. We should see how this one simplifies specifically. This is not in its simplified form because there's a fraction inside the square root of this one. But any questions with the last two that we solved so far? Okay, the last ones we solved, the way we solved them was we just put the fractions together and then we reduced the fraction. Here, the fraction's already here and it doesn't reduce in a clean way. So we want to take the opposite approach. Break this down as square root of 7 times the square root of 3. Now the problem with this one, the reason it's not simplified is because there's a square root in the denominator. So let's rewrite this as root 7 times root 3. And we're going to do a particular operation that has a name. This is called rationalizing the denominator. Hello. So the way we do that is, the thought is the denominator is a square root of 3, which is an irrational number. But if you multiply it by root 3, just like we saw in the last section, root 3 times root 3 is 3. Now it's a rational number. That's what we mean by rationalizing the denominator. Doesn't mean we're trying to reason with it or something like that. It just means we're trying to put in an actual rational number. So across the denominator, root 3 times root 3 gives us 3. Across the numerator, root 7 times root 3 gives us root 21. At this stage, the problem is over. So if we have a root with a fraction, this would be the strategy. Let's put this one on a new page so we can just keep all the concepts together for example 2. This one's kind of similar as well. This one has the square root of 3 in the denominator. Because of the root 3 below, it's considered non-simplified. It's kind of like with negative exponents. We always force our negative exponents to be positive because we're trying to standardize our answers. Answers can look very different depending on the sign of the exponents. And same kind of idea here. The number 3 over root 3 can have a very different form if we rationalize the denominator. And just so we can make everyone's answers look the same, so we can not get tricked into thinking values are different, we force this to have a standard form with a rationalized denominator. So we can rewrite this one as 3 over root 3 multiplied by root 3 over root 3, only because root 3 times root 3 would give us the 3 below. So now it's simplified by rationalizing the denominator. Across the numerator, it's just 3 times root 3. And that's where this problem would end. So they're all pretty similar in a certain sense. The only way they get slightly more tricky is if you have something like this, where their index is 4. I can't simplify this one just by multiplying by another fourth root of 4. That may not simplify in the way we expect. So probably a better strategy for this one is let's rewrite this by saying this is 5 times the fourth root of 2 to the power 2. We want to take advantage of a factorization here because now this tells us the way we rationalize this one is we just need something to occur 4 times. 2 has occurred as a factor twice already. So strategy is to take fourth root of 2 squared again in numerator and denominator. If we go that route, we'll have 5 times fourth root of 2 squared up in the numerator. In the denominator, it's fourth root of 2 squared times the fourth root of 2 squared. But the radicands multiply together, that's 2 squared times 2 squared for 2 to the power 4. So now the index of 4 will divide that index of, or that exponent of 4, and this just leaves 2 in the denominator now. The numerator is 5 times the fourth root of 2 squared, which is 4, and that's where this problem would end. This would be its most simplified form. And, now that I'm looking at this notes a little more clearly, one thing I should have done is just cancel those 3's on this one to give us a root 3. So the word simplified is kind of overloaded. It has a lot of meanings versus different contexts. To some people, root 7/3 feels more simplified to this because the number just seems bigger. But we're going for expression that doesn't have a fraction inside the square root. Well, this one, if we insist that the denominator is a rational number, 3 over root 3 is the same numerical quantity as square root 3, and that does look more simplified in my opinion. There's no fraction here whatsoever. But this one, The left-hand side, just on face value, isn't as complex, 5 over the 4th root of 4, as 5 times the 4th root of 4 divided by 2. There's just an extra thing going on here, that extra factor of 2 in the denominator. But to standardize answers, to insist that all denominators are rational numbers, we cleared out the irrational number in this denominator by rationalizing the denominator in the same way, just like we did over here. We did it over here on this step as well. We get an answer that looks a little bit different, but at least it's standardized now in that sense. Well, any questions with these group of 3 here? Okay, well, the next concept, oh, not quite the next concept, the next part is handling something that's a little bit more built up, something that's going to simplify a little bit further. On this one here, we could try to split it up and rationalize the denominator, just like we did the 7/3. We immediately split it up, multiply by root 3 over root 3. But this one actually reduces. So a good call on this one is just reduce the fraction first, then worry about rationalizing the denominator. 10 and 15 can be reduced by dividing by 5, leaving 3 halves. X power 3 divides into x power 11, leaving x power 8. Then we can take the root of 3 x power 8 in the numerator, divide by the square root of 2 in the denominator, and x power 8 is kind of a bonus in this problem. That part simplifies immediately to an x power 4, leaving behind the square root of 3, and the denominator is the square root of 2. At this stage, we did a lot of good work on this, but it's still not simplified, only because if we go to the list of what does it mean to be simplified, no radicals are in the denominator of a fraction. We have a fraction and we have a radical root 2 in the denominator. So we rationalize the denominator again on this one. Rationalize the denominator. But because this one's a square root, it's not so bad. We just multiply by the square root of 2, divide by the square root of 2. Next, multiply across the numerator. This will be x power 4, multiplied by the square root of 6. Let me rewrite that x power 4. It almost looks, if you look at it just wrong, like we're saying the 4th root of 3. So that makes it a little bit more clear. Root 2 times root 2 in the denominator just gives us 2 altogether. So now we simplified the radical. Down here we simplified a good amount, but we also simplified further by rationalizing the denominator to that step here. So that's how the second grouping of problems go. Any last questions on getting through this set? Okay, the notes are in fact almost over, but there's one thing that we didn't talk about how to simplify, and that was something that looked like this, 7 divided by 3 root 2. It turns out multiplying by root 2 over root 2 doesn't work for this one because root 2 would distribute. It would give us a 2 here, but when it multiplies to here, you would get 3 root 2, and you have the same problem. There'd be a root in the denominator. So that's what this next grouping of problems are going to be all about. We'll show exactly how to simplify these. And the hint to this is we just multiply by the conjugate. So this will be the concept that we come back to when we're in Tuesday's class. Multiply by the conjugate to simplify. We got a little bit further into these notes than I thought we would get, but this will be a good part to come back to. When we come back on Tuesday, we're also changing up to slightly different kinds of topics. This has been kind of a big review on just simplifying square roots at its heart. And the next section, 8.6, we're going to put to good use. We'll start solving equations that involve square roots in the very first place, and also look into the notion of what do we mean by a complex number? What does it mean to look into something like square root of -5, for example? But these will be the concepts we come back to next time. Have a good one. We'll see you next Tuesday.